is it's providing evidence not only of accelerated nuclear decay, but also evidence of catastrophic geological processes. Some of the processes that the conventional scientific community say take millions and millions of years to occur, and which are commonly brought up as accusations against believing in a biblical young age for the Earth timescale. So let me explain this fairly simply. You all know what a granite is, I hope. Here's a photograph of a road cut of a granite east of San Diego, not far from the Institute for Creation Research, up along I-8. And in the granite, that's a close-up view, you can see there's light minerals and there's a dark mineral. And the dark mineral is a flaky mineral, a black mineral called, a mica mineral called biotite. Biotite. It's very common in granites, and you see them in granites here in Colorado as well. And in these biotite flakes, embedded in them are tiny zircon crystals. Some of you are familiar with zircon. We mentioned it in the last lecture. It's zirconium silicate. The mineral zirconium silicate called zircon. And the zircon atom is the same size, more or less the same size as the uranium atom. So occasionally a uranium atom substitutes in the zircon lattice, crystal lattice. And so zircon crystals contain radioactive uranium atoms within them. Over time, the nuclei of those uranium atoms become unstable and they decay by alpha decay. And alpha decay is actually the two neutrons and two protons within the nucleus of the uranium atom are ejected together from the nucleus as a particle. And we call that an alpha particle. Two neutrons and two protons. So in other words, the size of the uranium nucleus gets smaller because it was originally 238 particles and ejects 4 of those particles. And we call those 4 an alpha particle. Now, not only does this happen once, where the uranium atom is unstable and it ejects an alpha particle to produce a daughter atom, but it happens more than once. The daughter atom, the first daughter atom, is also unstable, and it ejects another alpha particle and produces another daughter atom. In fact, it happens 8 times before you get down to a stable lead atom. Okay, so when uranium decays to lead, it actually goes through a whole series of these alpha decays, 8 in fact, and a number of beta decays in between. So it goes from uranium-238 down to lead-206. It's actually lost 32 of the original nuclei particles in the nucleus until it becomes stable as lead. So there are a total of 8 decay steps where alpha particles are ejected from a uranium atom before it's transformed into a stable lead atom. Okay, when the zircon crystals are large, say 60 microns, that's 60 millionths of a metre long, that's about the thickness of a hair, the alpha particles, when they're ejected, do not escape from the zircon crystal. Okay? These alpha particles can't escape, but they capture electrons and become helium atoms. And you're all familiar with Russ Humphrey's work on helium within zircons. The helium has actually come from the alpha particles produced by uranium decay. Okay, so alpha particles are actually in the same as the nuclei of helium atoms, without the electrons orbiting them. But when the zircon crystal is much, much smaller, only 1 micron in size, that is, a 50th or a 60th the size of the larger zircon crystals, the alpha particles actually escape. They escape from the zircon crystal into the surrounding biotite crystal. Okay? And so they're like little bullets. If you get a gun and fly it into particle board or what do you call it? Drywall board. We call it gyprock in Australia. But it's the sheets that you put up on the frame and the inside of your house. You leave a hole in it if you fire a bullet through it. Well, imagine what it's doing. These alpha particles are like little bullets that are shooting out from the zircon crystal in the centre there into the surrounding biotite flake. And what happens? You get a discoloration of the crystal structure in the biotite. See that? You can see in the centre there a tiny little zircon crystal, and you can see this halo of damage produced by the radioactive decay. The alpha particles shooting out from the uranium in that zircon crystal. So this discoloured area is called a radioactive halo, which is abbreviated to radiohalo. Now, we see on the screen, this is in 2 dimension, it just looks flat. But remember, the zircon crystal is the alpha particles are shooting out in every direction. It's actually a sphere of discoloration, and we've just sliced through it to look at it under the microscope and take this photograph. Okay, so here's our tiny little zircon crystal. It contains uranium. It's spitting out these alpha particles, but at each of these decay steps, where uranium-238 decays through 8 steps before it gets down to lead-206, each of those alpha particles have different energies at each of those 8 steps. So it's like having a handgun and a shotgun, a high-powered rifle with different, able to shoot the bullets further or not so far according to the energy. And so you can see what happens. Most of the damage to the crystal is done when the bullets stop. So the more powerful the bullets, the further they go, they leave a ring further out for bullets that don't go as far. And so you get a uranium radiohalo, where you know that there was uranium in the centre, produces 8 rings. The distances from the zircon are equivalent to the energies of the alpha particles, and you can actually work out which step in the decay from uranium down to lead produced each of those rings. So you've got the first decay step is when uranium-238 decays down to uranium-234. That has that top energy, and you can see it's one of the weaker decays, and it forms a ring closer into the zircon. But the step from polonium-218 down to polonium-214 is 50% more energetic, and so it has a ring further out. So this is significant. You can actually not only see the physical evidence that there has been radioactive decay, because you see some creationists used to argue maybe there wasn't any radioactive decay, that the chemical analyses have just been interpreted by the geologists as radioactive dates. Maybe there wasn't any radioactive decay. Well, the radiohalos are physical evidence that radioactive decay has occurred in the rocks. So the alpha particles ejected at each of the different decay steps of uranium have different energy, so these bullets travel different distances into the surrounding biotite, ideally producing 8 different rings in what then becomes known as a uranium radiohalo, because the parent of these alpha particles was uranium in that zircon crystal. Okay, I hope you're following me there. And there's a photograph of one of these fully formed dark uranium radiohalos with 8 rings. Now the biotite looks black in a hand specimen, but under the microscope it can look green or brown or orange, as you can see here. because it's so thin, light can pass through it. Now, it has been determined that to fully form a dark uranium radiohalo requires 500 million to a billion alpha particles to get the intensity of the damage to the biotite crystal so that it's visible under the microscope. You need at least 500 million to a billion alpha decays. And that is equivalent to 100 million years worth of radioactive decay at today's measured rates. So when you see that radiohalo under the microscope in a granite, it means that there has been so much radioactive decay, it's the equivalent of at least 100 million years worth at today's measured rates. Now, that's not to say there was 100 million years worth of decay. It's just that number of alpha particles equivalent to that amount of decay. And that's important to remember the difference. That's why you'll always see in brackets at today's decay rate. That's assuming today's slow rate of decay. Now, granites around the world contain these dark uranium radiohalos. And there's a number of granites that I've looked at in the Grand Canyon, in southern Australia, in southeastern Australia, in the Lake District of England. In fact, I'm going to talk about that granite in a paper at the conference in Pittsburgh next month. And in Stone Mountain in Georgia, where the Confederate Memorial is, we see granite that contains uranium radiohalos. And the Half Dome granite in Yosemite National Park, the biotite in it contains uranium radiohalos. So granites contain observable physical evidence of abundant nuclear decay, at least 100 million years worth at today's decay rates. However, in the same granites, in the same biotite flakes, with the uranium radiohalos, we find other types of radiohalos. Now, the big one there is, it looks so blurred, take my word for it, it's a uranium radiohalo, the big one you see there on the left. Okay? The reason why it's so blurred is because there's been more than 100 million years worth of decay involved. There's been so many alpha particles, the rings have become blurred. It's just become a mass of alteration, damage to the crystal. But next to it, you can see a much smaller radiohalo that only has one small ring, an outer ring, and everything inside of it is dark from the alteration. It consists of only one ring and it's smaller. Then we go to other biotite flakes where we see radiohalos that consist of two rings. And take my word for it, there is a lighter outer ring of that other radiohalo in the crack. So you get one ring radiohalos, two ring radiohalos, whereas the uranium has 8 rings. We also find radiohalos that consist of only 3 rings. And there are 3 rings there. It doesn't show up well on the screen. But in the blurred area of that central dark area, there are actually 2 rings close together, and there is an outer ring. Now, because we can measure the radii, or the diameter of those rings, we can actually work out what elements were responsible. The top right-hand corner, we see a cut-down version of the earlier diagram with the 8 rings of a uranium radiohalo. Okay, and again the same list of parent and the energies. Look at the rings where we have the 1 ring, the 2 ring and the 3 rings. They correspond to the last 3 isotopes in the decay chain, the 3 polonium isotopes, polonium-218, 214 and 210. Now, the 1 ring halo only has the ring for polonium-210, so we call that a polonium-210 halo. The red one, the bottom left here, it has two rings, the ring for polonium-210 and the ring for polonium-214, so we call that a polonium-214 halo. And the one with the three rings has the ring for polonium-218, 214 and 210, so we call that a polonium-218 halo. Now, why do we give it those names? Well, think about it. Why did we call the 8-ring one a uranium radiohalo? Because it was parented by uranium in the zircon in the centre. And the uranium gave rise to all 8 steps. So, if there was only one ring produced and it was a polonium-210 ring, what must have been in the centre? Only polonium-210. If we have two rings and it produced the 214 and the 218 rings, because you go down the decay chain, okay, it means that you only had originally polonium-214 in the centre. Why? Well, if you had polonium-214 in the centre, it would decay to 210 and produce the 214 ring, and then the 210 would decay and produce the 210 ring. I see a few heads nodding, so that means at least a few of you are following what I'm saying. And if you've got three rings, the 218 would have to have been in the centre to decay to 214 to decay to 218 to produce the other two rings, to get all three rings. So you follow what I'm saying? These radiohalos are easily identified as produced by the alpha particles from the last three decay steps, parented by those three isotopes of the rare element called polonium. By the way, it was discovered by Marie Curie, who named it after her native home of Poland. So that's the derivation of that name, polonium. Now, so far so good. That's easy to understand. What's the big deal? These polonium radiohalos are found with uranium radiohalos in many granites around the world. This is what I did in my research, looking at these biotite flakes, say in the ruined granite of Arizona, or this granite in South Australia, the Shap granite in England, the granite east of San Diego. All of these granites had both uranium and polonium radiohalos in them. Big deal. Well, these polonium radiohalos, however, were described in a very famous US court case as a very tiny mystery. Why are they a very tiny mystery? By the way, the gentleman who made that comment at the time was the Deputy Director of the US Geological Survey, and arguably at the time the world's leading expert in potassium argon dating. He now works at the University of California, Berkeley radioactive dating laboratory. Why did he call these a very tiny mystery? Well, the answer is simple. These three isotopes of polonium are very unstable and they only have fleeting existences. They have very fast decay rates. What are those decay rates? Polonium-210 only lasts on average for 138 days. Polonium-218 only lasts for 3.1 minutes. If you think that's fast, polonium-214 exists for 164 microseconds. You blink and it's gone. That's how fast it decays. In other words, if you started with 1 pound of polonium-214, in less than a second there'd be none left. That's how quickly it decays. So you can understand why these halos are a tiny mystery, because remember, the polonium-210 had to be in the centre of that polonium radiohalo, independent of uranium. If there was any uranium in there, you'd get the other rings. How could the polonium get to be in the centre of that radiohalo if the polonium only had a fleeting existence, measured in fractions of a second? Well, it means on the first thing is the polonium radiohalos had to form very rapidly. Okay? If it decayed so quickly, the alpha particles were produced so quickly, therefore the damage was occurred quickly, therefore the halos formed quickly. Now, Robert Gentry, who was the pioneer in this research, claimed that these polonium radiohalos were thus created and must be the fingerprints of creation. Why did he say that? Well, he claimed that there was no natural process capable of forming these polonium radiohalos because you need a concentration of at least 50% polonium in the radio centre, he said, all at once. In other words, you had to have, remember, you've got to produce between 500 million and 1 billion decays to make a visible halo. So you had to have between 500 million and 1 billion polonium atoms in the centre to produce that decay. And so he argued if it was there all at once, how would you get it all there at once if it only survived for a fraction of a second? He said, aha, God must have created it there in the rock. And he therefore said, okay, if the halos form rapidly, the polonium must have formed rapidly, and God must have created the polonium in place. Now, since this was in a granite, he claimed that these granites were also therefore created. Okay? However, why did God create the polonium radiohalos and then allow the uranium radiohalos alongside of the biotite flakes to then form over millions of years in the same biotite flakes? It doesn't seem to make sense. Furthermore, the biotite flakes containing these coexistent polonium and uranium radiohalos are often found in granites that can be shown to have formed during Noah's flood, for example. At a paper I presented at the 2003 conference in Pittsburgh, International Conference on Creationism, I looked at the Stone Mountain granite, the granite east of San Diego, and one of the granites in Australia, where there is evidence that those granites have intruded into and cooled and altered rocks that contain fossils that would have formed during Noah's flood, implying that the granites were intruded into those rocks during Noah's flood. And then after the granite cooled, these radiohalos formed. So it could have nothing to do with God creating these halos or the polonium or the granites. So this means that we had to develop a new model for understanding how these polonium radiohalos could form. Well, the clue is this. Think about it. Here we have a uranium-238 halo down the bottom there. On the bottom right, we have a polonium-210 halo. It's in the same biotite flake. What is inside the uranium halo? What is at the centre? A zircon crystal. What's in the zircon crystal? Uranium. What is a byproduct of uranium decay? Polonium. The closest source of polonium to the polonium radiohalo is the polonium being produced by the zircon crystal at the centre of the... That's why the two are in the same biotite flake. And so this was a clue. Maybe the polonium has actually been derived from within the biotite flake from the zircon crystals containing the uranium nearby that is also at the same time producing the uranium radiohalo. Where did the polonium came from? It had to have come from the zircons, which are also generating the uranium radiohalos. So it's quite logical. The uranium is going to decay down to polonium before it gets to lead. What if some of that polonium was siphoned off or transported away from the zircon crystal to another location in the same biotite flake where it concentrated and then produced the polonium radiohalo? That makes a lot of sense. That's why they're in the same biotite flakes. But see, that's going to have lots of implications. This means, because it's in the same biotite flakes, the uranium and polonium radiohalos had to have formed at the same time. Now, one thing that we know about granites, when they cool, the hot granite rock has water in it. When it cools, the water comes out of solution in the molten rock, and it's part of the mechanism for carrying heat out of the granite into the surrounding rocks. A lot of the ore deposits, the metal deposits that we find on the Earth today that are associated with granites, are a result of the water flushing the metals out of the granite and causing the metals to concentrate in veins as gold, in gold deposits, or veins and tin deposits in Cornwall in England, gold deposits in veins out of granites associated with water. So water is produced by granites. Now, the biotite flakes are actually like the pages of a book. They're sheets of atoms that are stacked on top of one another. And just as you can peel apart the pages of a book, you can peel apart a biotite flake. This is a natural weakness. So as soon as you get water in the granite, after the crystals have all formed, water not only flows between the crystals, but it has a passage where it can flow between the sheets in the biotite crystal structure. And that's what I've illustrated on the side here. Looking at the side of the sheets, those lines across the page. Now, the zircon crystal is stuck between two of these sheets. Water flowing along there is going to pick up any polonium. Hot water actually is good at dissolving polonium. We actually find polonium in some volcanic waters. Interesting, polonium was also in the volcanic gases when Mount St Helens erupted, polonium-210, the longest lived of the polonium isotopes. And we find polonium in hot water springs on the ocean floor. So it can travel distances in hot water. We've actually measured that in the real world. The phosphate rock in Florida has background uranium in it, and polonium is in the groundwaters, and it travels for some miles in the groundwaters. So it's known to travel in water. So the water flows between the sheets. Uranium in the zircon crystal, you can see that there, is decaying to produce polonium. And notice the polonium radiohalo is on the same sheet, between the same sheets. Why? Because when we ripped it apart to look at under the microscope, there was the uranium radiohalo, there was the polonium. They're on the same page of the book. Okay, so that's another clue. But remember, the uranium decay has to deliver enough polonium to generate 500 million to 1 billion alpha particles to form each dark polonium radiohalo before the polonium decays. So you've got to transfer that much polonium from the zircon crystal across to form a polonium radiohalo nearby. That is at least 100 million years worth at today's rates of uranium decay has to have occurred within days to produce all the polonium before it decays to form the polonium radiohalo before the polonium was all gone. You follow what I'm saying? These two radiohalos have to form side by side at the same time. If the polonium comes from the zircon crystal by uranium decay, but the polonium radiohalo forms within days or hours, depending on which polonium atom it is, the uranium has to decay to produce that polonium. The uranium has to, while it's decaying, is producing the uranium halos, while it's producing the polonium to produce the polonium radiohalo. So that means 100 million years worth of uranium decay has to form in just a few hours, minutes or days while the uranium forms. See what I mean? This is evidence for accelerated nuclear decay of uranium. 100 million years worth of uranium decay in just a matter of days to form the polonium radiohalos right alongside. And we find this consistently in granites all around the world. And so that's why we concluded in the rate research that dark uranium radiohalos in many granites around the world are observable physical evidence that abundant nuclear decay has occurred at least 100 million years worth at today's decay rate. Coexisting uranium and polonium radiohalos in many granites around the